Now we can apply the root locus idea to the plant that we were working on previously in this lecture. So we have our open loop or plant transfer function, this 1 over s squared plus 2s. Now we want a specific performance out of our closed loop system when we put our feedback controller around it. So first, we've already selected the controller. We need to do that up front. For this example, we're going to use the P controller like we were using before. And we want, on the performance side, the closed loop transfer function to have a damping ratio of 0.5. Now, I'm selecting the P controller a little bit arbitrarily. We know it will work for this system because we just saw in the previous part of this example it did. And I'm arbitrarily selecting right now a damping ratio of 0.5. But where might the performance metrics come from? Where might our selection of zeta and omega n come from? Those are going to come from what we desire for maybe the peak time and the max overshoot as two examples, but we're usually going to select those first, and then from the selection of those values, select the natural frequency and damping ratio. So now we can look at all of the different gains that we could choose for this P controller system and see how it's going to affect the pole placement, and then the poles are going to affect the damping ratio and natural frequency. In this example, we're not going to be concerned about natural frequency, just the damping ratio. So going into MATLAB here, I have in this section, I'm defining this G0 term. That is, again, my plant. But really what I'm going to put into the root locus in general is what I was calling before that G prime, which is the plant times the controller without the gain. So looking back at this P controller system, we see that the plant, the 1 over s squared plus 2s, times the controller, which is k. If I don't include the k, then it's just 1. So that G prime is going to be 1 times my plant, which just gives me back my plant. Now, when we talk in the next segments about PD controllers or PID controllers, now the controller transfer function is not going to be simply 1, and we'll see what it looks like then. But for this P controller, yes, the controller is simply 1 until we choose K. So I'm doing the root locus on G0, which is, again, just 1 times G0. And here, just so we get a little bit better picture, I only want to test gains from 1 to 15, and I'm going to do it by integers, so 1, 2, 3, 4, 5, etc. Now I can leave that blank, or I can make 15 larger. I could put more detail here and not skip by 1, but for this particular example, these are the gains I want to try. But you can leave this whole section blank or put a lot more detail in, and we'll do that in subsequent examples. All right, so I'm using the rlocus command. I like to use the grid so I can see a little bit more detail about the natural frequencies and the damping ratio. And we'll tighten up the axis a little bit and make the font size different to make it a little bit easier to read. The default rlocus that comes out isn't necessarily the most readable. So I'm going to run this. And out comes this plot. This is the root locus. So if we see here what's illustrating, I have this blue line, I have this green line. They're both vertical in this case. The root locus is going to be, the shape of it is going to be determined by the transfer function that you put in. This one happens to be just this vertical line. And what is this representing? The blue line is one of the dominant poles, and the green line is the other that we can select from. Since they always come in complex conjugate pairs, one of them is going to be above this x-axis. This is the imaginary axis. And then the horizontal is the real axis. So really, we only ever have to look at one side vertically or the other, because if we choose one pole, we've automatically selected the other. We've automatically selected the complex conjugate value. So let's see what information this is giving us. So if I just click, we see if I drag this around, I can see the different poles I have to choose from. So actually, there's a lot of information that's in this little pop-up here. So in the little pop-up, specifically when we use rlocus, we can see the gain that that point represents, where the pole is located, and it gives us the damping and the overshoot and the natural frequency there. Again, the overshoot is going, and the natural frequency, those are being calculated based on the baseline second order system only, which in this case is going to be okay, but we'll see in the future that it's going to be a little bit different. All right, so if I have a gain of 1, we see that the poles that we choose from are going to be at -1. which we already know this to be true from before. If I drag this a little bit, I'm going up to what happens if k is equal to 2. Well, that puts the poles at -1 plus or minus 1i or 1j. Again, keep in mind if I go on the green side of here, I get where the other pole is, -1 minus 1j. Again, they're in complex conjugate pairs. If I select -1 plus 1j, I've automatically also selected -1 minus 1j. All right, and I can drag this through. Now I told it to only use these integer values of gain. I didn't have to. So you see it's skipping one over another. There are other values of gain I can choose between here. Just in this example, I'm going to ignore that. So let's see what's happening. The pole placement is going to determine the natural frequency and the damping ratio. So what's going to happen if I'm low, if I see some of the axes that are coming out here, the angle here is telling me about the damping ratio. So if I'm closer to the x-axis or the angle is smaller, my damping ratio is going to be higher. So here I have a damping ratio of 1, and then this line 0.86, 0.64, etc. So the bigger angle I'm making with that x-axis, the smaller my damping ratio is. However, on the other side, my distance from the origin is determining my natural frequency. So for this case, when I'm down low, like I have a frequency of 1.14, that's my distance from the origin here. And as I increase the gain, I'm getting further and further. The radius is increasing from the origin. So the frequency increases, like here, it's 2.65. Now we're going to see how we can modify the root locus in subsequent examples, but here, these lines are again showing me up to 15 at least, all the different poles that I have to choose from. I can't choose anything out here or in here because those are not appearing on the root locus. There's no amount of gain that I can pick that's going to let me pick from those poles. So back to what we were looking for in this example, we wanted specifically a damping ratio of 0.5. So that's going to mean that we need to choose a pole so that the angle is going to give us, or the damping ratio is 0.5. So if I drag this around here, we see the damping is 0.707, 0.577, and then here it is. Now I knew ahead of time that the gain of 4 was going to get me here, but had I made more gains to pick from, I would be able to zero in on it if 4 was not, if 0.5 was not exactly on the root locus point that I was picking. So knowing ahead of time that 0.5 was associated with a gain of 4, I was able to choose that point. And I'll drag this down. So this is telling me that in my system, in my closed loop system, if I pick k as 4, a gain of 4, that's going to put my poles, my dominant poles, at -1 plus minus 1.73 j, and that's going to result in a damping ratio of 0.5. If I have a damping ratio of 0.5, that's going to give me an overshoot of 16.3%. So let's put that into the controller that we've already been using. Again, revisiting it here, we're just using that same P controller, but now I'm not going to test a bunch of different gains out. That's what the root locus already did for us. I specifically know that I want to use a gain of 4 so that my damping ratio is 0.5. So I'm going to rerun my controller code only with a gain of 4 and see what the output and input look like. Right, so applying here my output and my input and the error, we're going to see that this is my output on top. Really what we can investigate here is what is the overshoot. So we see we have a peak value of 5.815. We have a steady state value by design of 5. So I can compute what my overshoot is by using really the percent difference. So 0.815 is my percent difference, divide by the steady state value, and really multiply that by 100. So my overshoot from the simulation I'm getting is 16.3%. And if I go back, I just want to check that again against the root locus, what it predicted. Going back to my root locus and selecting that gain of 4 again, it was saying that with a damping ratio of 0.5, the overshoot is 16.3. Well, we can make that calculation. We know how to calculate max overshoot from the damping ratio. So that should be expected, and we saw that in simulation from the Simulink that we confirmed this. Now if we looked again back to the root locus in general, for this particular one, we had the issue that the only way to increase the damping was to also decrease the natural frequency. Let's go back to the plot again, see this relationship. So to decrease the damping, I have to get further away. I have to make a bigger angle with the x-axis, but we see for this particular one with the vertical line that the poles lie on, by making that bigger and bigger angle, I'm also getting further from the origin. So the natural frequency increases as the damping ratio decreases. If I want a larger damping ratio, then I'm going to be making the natural frequency smaller. So the trade-off, and this is what we saw when we were just testing different values, there's that inverse relationship between natural frequency and damping ratio, and that's why we saw for this plant, putting it into the control system, the P controller at least, that if we wanted like a lower peak time, well, we had a higher max overshoot. If we want a lower max overshoot, we had to have a larger peak time. And possibly we want both to be smaller. But the problem we have right now from a graphical standpoint is ideally if we want both small, well, we can make the natural frequency larger but make the damping ratio remain the same if we were able to choose points over in this region. If I could just take this point, if I could go to the left here, I'm going to barely change what my damping ratio is, but I'm going to be able to increase my natural frequency. Or if I can go to the right, I could decrease my natural frequency without really affecting the damping ratio. But again, those points aren't on this root locus. So what happens if that is what we want? Well, if we want both to increase, or maybe both to decrease, because that would reduce the overshoot and the rise time. So ideally, if we could change the shape of this root locus and make it curve to the left, so we could select poles that give us a larger natural frequency and a larger damping ratio, that would be ideal. The P controller can't do this though. The root locus is showing us the only poles that we can choose from for any amount of gain. So what we're going to investigate next is what if we use a different controller? We're going to look at the PD controller, and that's going to give us the flexibility to actually change the shape of the root locus even though the plant is going to remain the same.